Hey guys, so this is the video that I promised you. I want to briefly go over the process of creating the finite state machine in Logisim as a circuit and go through all the steps that are needed. I expect you to know how a state diagram works. I won't go too much into detail. I just want to cover the terminology first. So every state diagram consists of states. As you can see, the circles represent one state. They usually have a name starting with S, so you can name them however you want, but usually they're named S and then just different numbers basically. So you start with S0, S1, etc. So this is called the state. We have transitions, which are the arrows between two states, or they can also start at one state and end at the same. If you that basically shows that no change in the state, or the state is not changed. And the text next to a transition is the event, basically what has to happen for that transition to trigger. If a transition triggers, then basically you have to be in the state where the transition starts. Once the event happens and the transition is triggered, you will end up in the state that the transition is pointing at. So this is just a brief recap. Now, basically, you have to do 5 steps to create the circuit for that finite state machine from the state diagram. So the first step, of course, is to create the actual state diagram. The second step is to encode each state, because as of now, the states have names like S1, S0, or banana, whatever. There can be any name. But of course, our circuit cannot process strings or anything. So we have to break it down into zeros and ones. The second step makes sure that you give each state a unique binary number. So if you only have 2 states, you could use 1 bit, which is then one state would be encoded with 0, the other state would be encoded with 1. If you have more than more than 2 states, then you need more bits to encode them. And it's basically the same ratio as you had with the select bits for the multiplexer and the number of inputs. So for 4 inputs, you need 2 bits to describe them. In our case, if you have 4 states, and you need 2 bits to encode each one of them. So basically, the number of combinations you can do with the number of bits is the maximum number of states that this finite state machine can have. The third step is creating the truth table with the inputs of the system. So anything that is needed for an event that triggers a transition and changes the state is an input. Anything that does not trigger, so basically that does not lead to a change in the state, is not an input of the finite state machine. You also have to use the current state that the finite state machine is in as an input. However, the difference of the current state, and that's the reason why I'm explicitly talking about it, the current state is generated by the FSM itself. So you don't have to have an actual input to that circuit. You just need the standard inputs to be that have a standard input for that subcircuit. And something similar is the same for the output. So something similar is happening with the outputs. So you list the output of the finite state machine. So whatever you want the finite state machine to basically output, you have as an actual output of that subcircuit. The next state is also one output, which is necessary to indicate what the behavior of the finite state machine is. And this next state is generated by the FSM itself. Okay, so that's the third step, creating the truth table. The fourth step is deriving the Boolean equation from the truth table for each of the outputs. That's exactly the same process as you've applied in project 2. So basically you have one equation for each output, and you create the terms for that one output, for the equation of that one output, by looking at the rows in the truth table where the output is true, so 1. And then you just write them down, those terms for each row that we have a 1 on the output, and OR them together. The fifth step is to create the actual circuit from a Boolean equation. Of course, that is also the same process as before, but there are a few extra things you have to do to create the finite state machine, or the FSM in short. All right, so let's go through those steps on one example. So the state diagram that we're looking at is pretty simple. It has one input and one output. So the input is X. You could imagine for this example that a button is connected to the input X. So whenever I press the button, I'll get X is equal 1. If I release it, then X would be equal to 0. The output in this case is Y. And you can imagine for this example that Y is connected to an LED. So as soon as the output Y is true or 1, the LED would light up, and if Y is false or 0, the LED would turn off. Okay, so here's the state diagram for this simple system. So what should happen is, as soon I have basically two different states that are visible to the user of the system. So the first state is, I named it here as 0, and in this case the output, so Y, our LED, is false, so it's off. So the user can observe that the LED is off. The second state is, at some point the LED might be on. So the second state, S1, has the output Y equals 1, and the LED is on. So these are the two states that you can observe when looking at the system. Now we have to figure out how we transition between those two states. So when does the LED turn on and when does it turn off or stay stay on? So this depends on how we press the button. So if the button is not pressed and we're in S0, basically we will stay inside that state. This transition here starts at S0 and ends at S0. So if that transition triggers, that just means we stay inside that state. The output won't change because we're still in that state. And this is the event, so if the button is not pressed, X is false, so not X, this transition will trigger and we stay in S0. Now, if we press the button, X will be true, so that this transition triggers, and we would change the state from S0 to S1. If we hold down the button, we will stay inside S1. So X is still true, we press the button, we stay in S1, and as you can see, the output here is Y equals 1, so our LED turns on as soon as we press the button and hold it down. Now if we release the button, and that's the last transition we have for the system, we would transition back to state S0 from S1, so the LED is on, we release the button and we go back. Here's the event, X, not X, so that means we don't press the button. And we're back in this state S0. So that's the description of that simple system. Now that's the first step. So basically you have to capture the behavior of that system as a state diagram. Now the next step is to create the truth table. And as I said, we need, as inputs, we need the actual finite state machine inputs. In our example, that was the button, X, that we can press, so this influences which state the system is in, and we need the current state of the finite state machine. This is actually the output of the register that we use inside the finite state machine to store the current state. So you can just take the output Q of that register. And again, this is the value that is generated by the finite state machine, so it's not an actual input to the whole circuit. As outputs, we have, of course, our finite state machine outputs. In our case, we have Y that turns on or off the LED that is connected. And we also need to know what is the next state after an event happened. And again, this is not an actual output of the finite state machine. This is just for internal use to store it into the state register, because the state register then takes on the value of the next state, and this changes the behavior. So depending on the state we're in, the system reacts differently to the same events. That's the unique thing about the finite state machine. So make sure to add the next state and the current state to your truth tables besides your determined inputs and outputs. All right, so we have our example from before. Now, the next thing that we have to do is we have to encode the states. As I mentioned, we're working with circuits, so the circuits can only understand ones and zeros. So if we have a description and name like S0, or again you can name it bananas and apple, or LED is off, LED is on, we have to transition it over to a binary number, otherwise our system cannot understand it. And that's the reason why you have to encode each state. So as you can see, the left column is the state name, S0, S1, or bananas and apples, or LED is on, LED is off. The other way around, LED is off, LED is on. We need to transition that to a binary number that represents each state. In our case, we only have two states, so we can represent it with 1 bit, and we just define out of convenience, S0 has the binary value 0, S1 has the binary value 1. Again, the encoding is totally up to you. You can choose even more bits if you want. You can use 4 bits, and you can encode them with 4 ones. You can encode S0 with 4 ones if you want to, and S1 with 4 zeros. It doesn't matter. It's just important that you have a unique binary pattern for each state. And of course, the less bits you use, the easier the circuit gets. So in case of 2 states, stick with 1 bit. It's easier. Now the next step is you create the truth table. So as you can see, we have the X here, which is our input of the finite state machine, and I've already put in the different combinations that are possible. And we have our current state. So this is the information of the which state we're in right now. And these are the inputs to that finite state machine. S is generated internally, X comes from outside. And as you can see, I have 4 rows that represent every possible combination of those 2 inputs. Now we have Y, which is our output of the system. Remember, they are inside those circles of the states. And we have N, which is the next state. Since we only have one bit that describes the current state and the next state, this is just one column. If you have multiple bits describing a single state, encoding a single state, then you need more columns for the current state. So we would have S0 and S1. And also for the next state, we would need 2 bits to describe which state comes after the current one. So we would have 2 columns for that too, N0 and N1. All right, so now that we have the truth table with the input, the current state, the output, and the next state, we're just going to go ahead and fill out the missing output values. And you can do that by just simply going and walking through the state machine to figure out what these are. So at first, we have pointers. I should have explained while the red arrow was pointing at each column. Never mind. All right, so what are you going to do is basically you go into the first row, and we are in state 0. That means we are in state S0. Remember, we have the decoded value 0 for S0, and X is not pressed. So that means we're in state 0 and X is not pressed. The only transition that can trigger in this situation is this one up here, because this doesn't start in this transition doesn't start in this state. Only those 2 transitions start in our state S0, and this transition is related to a complete different state. So we can only start from transitions. Transition can only trigger that start from S0. Since X is equal to 0, that means only this transition triggers. So we stay as where we are, and the output is 0. So for the output, we know that if we're in state 0, will be 0. And if we're in state S1, we know that the state will be, the output will be 1, because we have the Y equals 1 down here in the state. Now, the first transition we see up here, highlighted in red, is the one that corresponds to the first line. Remember, we talked about being in state 0 and X is not pressed. So the next state that we have to fill now is the same. So we stay in the same state. So the next state would be 0. Now we go to the next transition. So we're still in state 0 here, but this time X is pressed. That means this transition would trigger. So our next state would be S1. and we encoded that with binary 1, so that means we will get a 1 over here. So then we go to the next transition. So let's look at this transition down here. We are in state S1, as you can see, state 1, and X is not pressed. That means this transition will trigger. Now, the next state in this case would be 0, since we're moving from S1 to S0. And now the last transition that is missing is the one over here. We are in state 1, and X is pressed. So this means this transition will trigger as long as we press down the button. That means the next state will still be 1 because we will stay in the same state. So this is basically how you walk through. You look at the left side of the inputs, you look at the state that is indicated, you look at the event of the input. So what is the input? What will the input's value be? And then you check basically which transition would trigger. And then you check what is the output of the current state and list that here. So for S0, this will be all zeros here. And for S1, we know Y will be true. So we have all ones here. And then you always check which would be the next state, which transition triggers. All right. Now, the next thing is, once you are finished with the truth table, you derive the Boolean equation. Again, this is the same as before. So we're looking now for the equation for n. So we're looking at the value number 1 on the output, and then describe based on the inputs, derive the minterms with both inputs. So in this case, we have s as an input and x as input, and it would be not s and x. Now the second one down here, we have s and x. So this would be another minterm. You combine them you can combine them to one Boolean equation using the OR operator, and then you have your description of the output. In this case, you can simplify it pretty significantly, so you can basically get rid of the s, and it would be that the next state equals if the button is pressed or not, so the input x. And the same for y. If you look closely, y is exact. So if you look at this whole column is exactly the same as this column. So you can just tell that it's y equals s. If you would do it the proper way, or how the process works, then you would derive s, not x. And for the second one, you would have s and x. And then you can, again, remove x from the equation like up here. But with s in this case. So we end up with y equals s. All right, so these are the two Boolean equations that describe the circuit. And you can use those to create your finite state machine inside Logism. For making it a little bit harder in the circuit, we're going to stick with the upper equation for the next state. So it's not too easy and not too simple. So even though we could use the simple version, we will kind of stick to this equation here and use that for creating the circuit. Now, if you're creating a controller for a finite state machine, so the circuit in Logism that represents the behavior of that finite state machine, there's two important things that you have to, or two major parts of each controller. So one is the actual state register. This is the component that stores the value stores the current state. And you have the combinational logic, which is the part that calculates your output and your next state. So here's one example that is not related to the example we're discussing in this video. Just to indicate, this is the state register up here. So you're storing information, this is the next state and the current state in here. And this is the combinational logic, which calculates, in this case, the value of the next state. All right, so let's create the circuit in Logism. I'm going to switch over to Logism. I've already put in the equations that we derived from the truth table. So the first thing you should do is add the state register. So that's under memory. You have the register because this is essential. Without that, the state machine wouldn't work. Notice that the initial size of the state register is 8 bits. We only need 1 in our case. This up here is the input D, so whatever value is attached to this input will be stored. Q is the output, so that's the current register's value. This is an enable bit, so we won't attach anything to it because we want the register to work all the time. And down here we have the clock, so we need a clock in order to make the register work. Remember, the register only stores values when we have a rising edge. That's the default configuration. So if we go to, I always have to look for it, under wiring, we have the clock, which is this part, and we attach it to this input, which is important. Now you can manually toggle the clock here, but I would recommend pressing, going to simulate and ticks enabled. Then you can see the clock starts ticking. You can also do Command K or Control K to start and stop the clock. We're going to stop it for now. Now, as I said in the video before on the slides, the output of that register, the state register that we have, is the current state. So I'm going to add a label saying current state, and we had, let's do that in brackets, and we had the current state as S. Now the input of that register, which is D, is the next state. So this is the information, the input that we generate ourselves inside the finite state machine. So again, I'm going to add the label N for next state. All right, so this will be the next state, because the next tick, this information will be stored, and then we will see that on the output here. So we need inputs. We have the button X, so we need that as an actual input to that circuit because we have to attach it somewhere. So we're going to add this input, and we have the output. Remember, we want to light up an LED, so this will be the LED, and that's our output Y. Okay, so this is the initial setup for almost every finite state machine, listing the inputs, having state register, we have the current state, the next state, you need the clock, you need also to activate it once you test your circuit, and we need the outputs. Now, what happens is that we're just gonna now create the combinational circuits to have the circuit for those two outputs that we just derived from the truth table. Let's start with the simple one, Y equals S. That's the easy one because it's no actual gate is needed. So S is our current state, this is this line, and Y is the output. So the only thing that we have to do in this case is connect it to the output. So done. Now the more complicated one is the next state. Now we have two AND gates with each two inputs. So we're gonna add those. Grab an AND gate. I'm gonna turn them south. Change the number of inputs to 2, and we can also do a smaller one, and we need 2 of those, so I'm gonna add them here. Now one thing I like to do is, oh actually no, I'm letting face them east. Alright, and I explain why, because that's usually a layout that worked well for me, so that's a recommendation. Create basically a bus, not a real bus, but like a layout bus in the circuit. So I'm gonna drag down one line, which is S, and I wanna drag down another line, which is X. So left side S, right side X. This is the only information that we need, or the only inputs that we need for this equation to get N. So the first thing is we need not S and X. There's actually a handy thing you can invert. If you click on a gate, you can click if you look at the properties, you can invert single inputs. So if I say negate the top one, a circle will appear, and that's basically the NOT gate. That's the same as adding this in front, but it's a lot smaller and a lot easier. So my recommendation, use it. So we want to have not S. This is our S, not S, and X. So we're going to connect those. And for the second term, we have S and X, so we don't need any inverters. We just connect both of them to the AND gates. Now, both of those terms are OR together, and then we have the result N. So we need an OR gate. I'll add it here. Again, inputs 2, I'm going to switch it to a smaller one. And basically the OR gate combines the two results of the AND gates. So I'm just going to connect the AND gates to that OR gate. And there you go. That's basically it. So this here is N. The output here is the next state. Now, this is the next state of, the next state is basically the input of that register. So the only thing that's left that we have to do is connect those wires, and off you go. Now, in order to make sure that everything works as expected, I always recommend you stay in that view. Don't use this state machine as a sub-circuit now, but rather go ahead and play around and see if everything works. Now, toggle on the clock. So we don't press the button, the LED is not on. Cool, works. Now I press the button, as we can see, the LED goes on, and as long as I hold it down, basically, the LED stays on. As soon as I release the button and the next rising edge of the clock comes, we will reset and the LED turns off. And you can see that. So if you look closely, when I activate it, you can see that the next state will be 1, which is then stored inside. If I disable X now, what instantly happens is that the next state will be 0. So this wire running all the way back to the input of the register will be dark, and with the next tick of the clock, it will be the next state on the output on Q. So let's see if I can time that right. I'll try again. So as you can see, it takes a little until it updates the output until the rising edge of the clock. If we can do it manually, then it's even easier to see. So we have the rising edge, we update it. Now I disconnect the button. Instantly, the next state updates to 0. So we know that the next state will be 0, but it's not taking in the number because we don't have a rising edge yet. If I have initiate the rising edge, then the register will update and store that info in there. All right, so that's how you create a finite state machine in Logisim. That's a wrong slide set. All right, so just a recap for everything. Again, we need 5 steps. Create the state diagram, encode each state, create the truth table with all the inputs that you need, and the current state. You have to add that. List also in the truth table the outputs and what the next state will be. This is important to make the FSM work. Next step, once you have the truth table, derive the Boolean equations from the truth table for each output. And create the circuit from the Boolean equation with the addition of the state register and the clock. All right, hopefully that helps you a little bit to understand how, or understand the process better, how to create the actual controller in the circuit from state diagram.